Good morning to all of you. Thank you, Rahul, for giving nice introduction. But above all, I am ADMA member. That is my introduction. Because what I learned and I reach to this position, I cannot forget the benefit which I received in last 13 years. I am associated with ADMA since its inception. The annual conferences of ADMA remained very much fruitful for me as well as my students, because here what we present and the reference we include as citation, most of the authors are sitting in the audience. The ADMA nurtured by giants like Professor E. Sampath Kumar, Professor Balakrishnan S. Arumugam, led Dr. B.D. Acharya, Mukti Acharya, and G. Ravindra. So, what I believe, the ADMA conferences are more focused, and those who want to work in graph theory and related concepts, they should never miss the annual conference of ADMA. And sometimes when we present our work from this on this platform, then it provides us the reason to broaden our vision, because when we present something, then people may suggest to give example or counter example, or to specialize the thing, or what are the new directions and dimensions that we can come to know due to such conferences. So, it is my suggestion to all the budding researchers to attend all the proceedings very seriously, because what I learn is due to the annual conferences. With this introduction, I would like to focus on today's topic, graph energy and related concepts. As it is rightly said that mathematics passes not only the truth but supreme beauty, and the same type of things and the characteristics is preserved by graph theory. Why the study of graph theory is important nowadays? Because it has many diversified applications. What I am going to present today is the concept which is a frontier between chemistry and mathematics. So, this is the plan of my presentation. So, theory of graphs, as just now we had a talk of Dr. Patra, that the things are related with the connectivity of objects. How they are connected, that is the important issue in graph theory. In chemical graph theory, it is a branch of mathematical chemistry that is connected with all consequences of connectivity in a chemical graph. And such graphs are very much useful to understand the molecule and the related concepts of transformations for any chemist. So, here when we consider any chemical graph, and this graph provides certain idea about the energy and the structural properties of various compounds. So, every chemical molecule can be represented by means of corresponding molecular graphs which represent the constitution of molecule. This is a propane C3H8, and there is a molecular graph of propane. One more graph, molecular graph we consider, it is of cyclopropane. So, each vertex of the graph corresponds to an atom of the molecule, and two vertices are adjacent if there is a bond between corresponding molecules. To simplify the handling of molecular graph, every carbon atom is represented by a vertex and carbon-carbon bond by an edge, while hydrogen atoms are ignored. The neglects of hydrogen atom cannot be a cause of any ambiguity, and such graphs are known as hydrogen suppressed graph. Here propane and its hydrogen suppressed graph is shown, while here cyclopropane and its hydrogen suppressed graph is shown. So, the energy of graph is defined with the help of hydrogen suppressed graph of a molecular graph. So, the concept of adjacency matrix is very well known to us, and the spectrum. The eigenvalue of adjacency matrix of graph is known as eigenvalues of graph, and the set of eigenvalues of the graph with their multiplicities. The first row is the list of eigenvalues, while the second row shows the multiplicity of the corresponding eigenvalues, and this list is known as the spectrum of G. Now, graph energy. For any graph G, the sum of absolute values of the eigenvalues of G is defined as the energy of a graph. Why the term energy is used? Because the pi electron energy of any molecule will be same as this, and that is why this is the way to study chemistry with help of mathematics. Without entering in a laboratory, we can have the idea of energy of a molecular graph. And the concept of energy was introduced by Gutmann in 1978. I also suggest those who want to read the introductory thing on graph energy. There is a book by Professor Balkrishnan and Ranganathan. I learned the basic concept from that. And many other books are also there. So it was introduced by Gutmann. He is from Serbia and he is the man of chemistry. Now, the question is this: if we know the energy of a given graph, then in chemistry there are various chemical reactions are taking place. One of it is an important is the polymerization. Means the various molecules are gathered and some new things are formed. Now, we are here using the concept of graph theory, that if we know the energy of a given graph, then if certain graph operations are applied to the given graph, then how the energy is affected, or how the energy of a given graph and the new graph can be related. That is the question. So, how energy is affected by various graph operations. For that, we consider the graph operation, splitting of graph. The splitting of graph G is obtained by adding to each vertex V a new vertex V dash, such that V dash is adjacent to every vertex that is adjacent to V in G. So, that is known as splitting of graph G. If we consider as an example to understand the definition, the cycle C4, and this is the splitting of C4.
Is this the same concept used in MyCSV construction?
Yeah. Then one more operation we consider, the shadow graph. The shadow graph of a graph G, denoted as D2G, is constructed by taking two copies of G by G dash and G double dash, and join each vertex of U dash in G dash to the neighbors of the corresponding vertex U double dash in G double dash. Let us have the example with help of cycle C4, and here the shadow graph of C4 is shown. Now, M splitting graph. Instead of taking only one vertex, we can take arbitrary number of vertices and construct its splitting graph. If we are taking m vertices at a time, then it is called the n splitting graph of a given graph. C4, and here 2 splitting is shown. in an analogous way, we can also have the M shadow graph. We consider the M copies of the given graph, and we construct the shadow graph is known as the M shadow graph of a given graph. Here we have taken 3 copies of C4 and constructing its 3 shadow graph. Now, if we have any graph G, then energy of the shadow graph is √5 times energy of graph G or any graph. So, I was using and studying labeling and domination in this way, but when I started to work on graph energy, I thought that can we use this knowledge into the research work of graph energy or not. Then we started by considering only one shadow, but that is why this result is there. But immediately after that, we generalized the thing by considering the splitting here. This is the splitting, one splitting, when here M splitting. When we have M is equal to 1, then the previous result is its corollary. But we have started with that, and then we come to this, and that's why it is stated there. How can we prove this? So these are the notations. V1, V2 up to Vn be the vertices, and the adjacency matrix is this. And these are the vertices of the corresponding to each Vi, which are added in G by to construct the M splitting of G. So, according to the definition of the M splitting, the neighborhood of these vertices will be same, because we have defined in that way. Now, the adjacency matrix, because we want to find the eigenvalues of the adjacency matrix of the newly constructed graph, that is M splitting of graph G. So, that we can write using the block matrix here. It is AG means the adjacency matrix of G, and that is the 0 matrix. And using the properties of the block matrices, we have this second thing here. Now, we will compute the eigenvalues of matrix A, which is shown here. Now, it is a matrix of rank 2. It has 2 non-zero eigenvalues. Say they are mu1 and mu2. And we consider A square because we require minimum 2 equations to eliminate mu1 and mu2. So, to obtain the values of mu1 and mu2. So, for that we consider square of A. And according to the properties of eigenvalues, mu1 square plus mu2 square is equal to 2m plus 1. It is the second equation, and solving these 2 equations, we have mu1 is this and mu2 is this. These are the 2 eigenvalues of A. So, this is the spectrum of A. M minus 1, 0 eigenvalues. 1 eigen means 1 plus root 1 plus 4m by 2 with multiplicity 1, and the last one with multiplicity 1. But as we have already mentioned, that the adjacency matrix of splitting graph, M splitting graph of G is the A cross AG, and that's why we have the spectrum of M splitting graph of G, where Mn minus n number of eigenvalues 0, n eigenvalues with the second one and the third one with this. So now we are able to calculate the energy of this graph. So it is like this, and the simple algebraic calculations establish the result that energy of M splitting graph of G is square root of 1 plus 4m times energy of the given graph. Now we state the thing here. We have spectra of cycle C4 is given by this, means its energy of C4 is 4, while energy of 2 splitting graph of C4 is 12. So just it is shown that how it works. Here M is 2 and we have this. Now similarly we have the shadow graph of G, then energy of shadow graph of the given graph is twice the energy of the given graph. And we have also generalized this result that if we have M shadow graph, then it is M times energy of given graph. Analogous way, we with the same notions and procedure we have employed in the result regarding the M splitting, we have reached to this thing. Here it is the adjacency matrix of M shadow graph, and this is this. So this gives us the energy of M shadow graph. Now the question arises again, is it possible that two graphs have the same energy, or is there any way to construct the equi-energetic graphs? The answer is yes. Or to identify the graphs whose energy is same as the energy of a particular graph. So to find the pairs of such graphs, if they are co-spectral graph, means spectra is same, then naturally they are equi-energetic because some of the eigenvalues will be same. So they are equi-energetic. Then we are interested to identify the graphs which are non-co-spectral, but the energy is same. So now we are focusing on this concept. This is the equi-energetic graph. Two non-isomorphic graphs G1 and G2 of same order are said to be equi-energetic if their energies are equal. So the concept was introduced by Gutmann, and in 2004 Ramane and others have proved that if G1 and G2 are regular graphs of same order, then their line graph LKG1, LKG2 and their complements are equi-energetic. Here this notation is called the iterated line graph. We take the line graph of a graph, again line graph, again line graph. So it is known as the iterated line graph. So, they established that if we have two graphs G1 and G2, then the iterated k iterated line graphs as well as their complements, they are equienergetic. What we, in continuation of our result established just now, we found that 2 splitting of any graph G and 3 shadow of graph G, they are equienergetic. Their energy will be same. Here 2 splitting of C4 and 3 splitting of C4. These 2 graphs are equienergetic. Now, extended shadow graph. Here, in extended shadow graph that we denote as D2 star G of a connected graph is constructed by taking 2 copies. There, what we have done in shadow graph, that we were just establishing the adjacency between the neighbors of the corresponding vertices. But here the vertices themselves are making adjacent, and it is known as the extended shadow graph. We can realize the things with help of this figure, that in a shadow graph we do not consider, we do not make or establish the adjacency between V1 and V1 dash. While here this adjacency between V1, V1 dash, V2, V2 dash, V3, V3 dash, V4, V4 dash and V5, V5 dash is also considered. And then again M shadow graph, if we employ the same operations by taking M copies of a given graph, then it is known as the extended M shadow graph. Here we have considered the 3 copies of C4 and its 3 shadow graph, extended shadow graph is shown. Now, let G be a graph with eigenvalues, this, and theta is the difference between the number of positive and negative eigenvalues of G. If it has 5 values positive, eigenvalues positive and 3 negative, then theta will be 2, like that. Then the energy of 2 extended shadow graph, means extended shadow graph, is 2 times energy of G plus n means number of vertices plus theta. Theta is the difference between the number of positive and negative eigenvalues of G. And the same type of result is established for extended M shadow graph. Then naturally the previous one will be the corollary of the second result, that M of M times energy of given graph G plus M minus 1 times n means number of vertices plus M minus 1 into theta. Then the extended shadow graph of G Cartesian product K2 and the energy of the shadow graph of extended shadow graph of G, they are equienergetic, their energy is same. Now, we have also proved one characterization, that is, if G is a bipartite graph, then the two extended shadow graph of G and the energy of the extended shadow graph of G and its extended shadow graph both will be same, but the absolute value of lambda I must means all of its eigenvalue must be greater than or equal to 3 by 4. If it is less than that, then this will not happen naturally. So, one more result is established. It also says that these two graphs are equi-energetic. If G1 and G2 are two graphs, then the extended shadow graph of G1 and this provided the all its eigenvalues are lambda I must be greater than or equal to 1/2, and the eigenvalue of the second graph must be greater than or equal to 1/2. The same thing is established for M extended shadow graph of graph G1 and G2. Then the next thing is border energetic graphs. The energy of complete graph is 2 into n minus 1. That is also established by Gutmann. In the same paper, he conjectured that among all the graphs with n vertices, the energy of a complete graph is maximum. Means energy of any other graph with n vertices cannot exceed with the energy of a complete graph. But soon after its conjecture, the conjecture was disproved by Walliker by giving some graphs whose energy exceeds than the energy of complete graph. Then the next discussion started. Are there any other graphs whose energy is same as the energy of complete graph? So, the graphs whose energy is same as the energy of complete graph, they are known as the border energetic graphs. So, the concept of border energetic graphs is recently introduced by Gong and others, and they termed such graphs as the border energetic graphs. Means the graphs whose energy is 2 into n minus 1. Now, non-border energetic graph means whose energy is same as the energy of complete graph. Line graph of K33. The line graph of K33 is a graph with non-vertices, and its spectrum is this. This is the convenient way to write the spectrum. Eigenvalue 1 with multiplicity 4. Eigenvalue 4 minus 2 with 4 and 1 with multiplicity 4. 4 with multiplicity 1, minus 2 with multiplicity 4 and 1 with multiplicity 4. So, its energy is 16, and the energy is its energy of K33 is same as the energy of K9, because the energy of complete graph with 9 vertices is 2 into 9 minus 1. This is the line graph of K33. line graph of Peterson graph. Peterson graph is very well known graph, and the line graph of Peterson graph is a graph with 15 vertices, and its spectrum is this. Eigenvalue 1 with 4 with multiplicity 1, minus 1 with multiplicity 4, eigenvalue 2 with multiplicity 5, and minus 2 with multiplicity 5. Its energy, if we have to sum the absolute values of these eigenvalues, it comes to 28, and its energy is same as the energy of K15. Means the line graph of a Peterson graph is also a border energy. This is the line graph of Peterson graph. Now, the important issue is enumeration of border energetic graph. For the given number of vertices, how many graphs are border energetic? It is surprising that there is no border energetic graph of order less than 7, means whose energy is same as the energy of K7. There is a unique border energetic graph of order 7. This is the only one. It is this graph. There are exactly 6 non-isomorphic graphs of order 8 which are border energetic. These are the graphs. These are these 6 graphs which are border energetic. Means its energy is same as the energy of some complete graph. There are 17 non-isomorphic border energetic graphs of order 9. These are this graph. And recently, Lee and others have proved that there are exactly 49 border energetic graphs with order 10. We can come to know that as we increase the number of vertices, then the number of border energetic graph this count will increase. Shao and Deng proved that there are 158 border energetic graphs of order 11, out of which 157 are connected and 1 is disconnected. There are 572 connected border energetic graphs of order 12. Now, using the same operations, we found that extended shadow graph of K and N is border energetic, means its energy is 2 into n minus 1. So, its border energetic graph of order 4n for any n greater than, means it is the energy of K4n, complete graph 4n, and this both are same. Here we are explaining this with help of this example. Extended shadow graph of K3 is border energetic. As why? Because its energy is 22 and energy of K12 is also 22. So, it is border energetic. Means A graph is border energetic if its energy is same as the energy of some complete graph. Energy of some complete graph. So here it is this. It is the extended shadow graph of K33. Now there are various variants of graph energy. If we have the Laplacian matrix, then we can have Laplacian energy, distance matrix and distance energy. Here we are considering the Fiddle graph, Fiddle matrix, and analogous way it is defined Fiddle energy, and we also study which graphs are Fiddle equienergetic, means their Fiddle equienergy are same. So we focus on that. This is the exacting one. This is the definition of a Fiddle matrix of a graph. So where the entries -1 if Vi is adjacent to Vj, 1 if not adjacent, otherwise it means Vi equal to Vj is equal to 0. Again, in analogous way we define the eigenvalues of these. They are known as the Fiddle eigenvalues of graph G. And Fiddle spectrum, it is a set of the Fiddle eigenvalues with their multiplicities. Then Fiddle energy, it is the sum of absolute Fiddle eigenvalues of graph G, absolute of this. So the Fiddle energy denoted as SEG, the sum of the absolute values of Fiddle eigenvalues of graph G. It was introduced by Hammers in 2012. So two non-isomorphic graphs G1 and G2 of same order are said to be Fiddle equienergetic if their Fiddle energy is same. Again, if they are Fiddle cospectral, they are obviously Fiddle equienergetic. So we are interested in the graphs which are Fiddle non-cospectral. Let G be a graph with Fiddle eigenvalues, there is sigma 1, sigma 2, and with this condition that all absolute values of all the Fiddle eigenvalues must exceed 10 1/2. Then again the theta is the difference between the number of positive and negative Fiddle eigenvalues of G. Then we have this result, that Fiddle energy of shadow graph of G will be this, twice Fiddle energy of G plus n means number of vertices, that is the order, plus theta is the number of difference between the number of positive and negative Fiddle eigenvalues of graph G. And we have also established the result for extended shadow graph of G. So the shadow graph of G and extended shadow graph of G are equi-energetic provided they have the same number of positive and negative eigenvalues, means theta is 0. Theta is 0. So, here we have this result. So, I am very much thankful for giving me the chance to present my work in my home state. Generally, in Gujarat, we do not organize or even invite any guest in this summer, because since last 2 months the temperature is average varying between 40 and sometimes 45, 45.9 and but Dr. Manish Gupta has accepted this challenge and organized the conference in its nicest way. And when I started my work and started to attend the conferences myself, or then from next year one of my students were attending the conferences. But day by day the number of contributed papers are increasing in ADMA conferences, and this time also out of 31 papers contributed to this conference, 18 are the research papers from Gujarat. Now my grand students are also presenting the papers, and that is again due to the platform provided here. So I am very much thankful for your patience listening. During January, February or like that. Can thank you all. Any questions?
Thank Professor Vaidya, and any questions?
Shall I remove this?
Professor Vaidya, Samir Vaidya, I am very happy that it is a very nice paper. You have considered the extension of graphs. You know what is the concave stuff? Suppose you are giving two graphs, G and H. A concatenation of two graphs is identify a point of G and a point of G and a point of H. We say that it is a concatenation of G and H. Suppose you take a graph G whose complement is also connected. So G and G bar are connected. Suppose you take a concatenation of G and G bar. It's also an extension of G to some other graph. Has anybody studied energy of concatenation of a connected graph such that whose complement is also connected? Is there anybody has, no, I think it is G and G bar, where G and complement is also connected. That I don't know. The idea comes to me. Because it's also an extension of the graph to a bigger graph, so that kind of thing can be studied. I don't know that.
Thank you.
Any other speakers? Sorry, questions? One more question.
You mentioned that line graph of K33 is equi-energetic with K9, right? See, line graph of K33 is isomorphic to the Cartesian product of K3 and K3. So in general, whether the line graph of KNN is equienergic to Kn Cartesian product Kn. Because here in the particular case n equal to 3, it is true. No, not iterated. It is line graph of K33 is isomorphic to the Cartesian product of K3 and K3. In general, line graph of KNN is isomorphic to the Cartesian product of Kn and Kn. So in the first case you say that they are equienergetic. So whether in this case also it is equienergetic. And again, you said the Peterson graph is border energetic. See, the line graph of K5 is the Peterson graph. So in general, line graph of Kn complement is border energetic with complete graph Kn. Because the isomorphism is there, so that's why I am asking. LK5 complement is the Peterson graph.
I think this so this with this there's
The tea break now, before which Professor Ravindra wants to make some announcement, I presume.
Professor Vaidya, your lecture is endowment lecture of Professor B.D. Acharya. His wife is here. And your 18 students today, out of 20, they are here. They are presenting the papers. Congratulations for this on behalf of
I am very much thankful for considering this lecture as a Professor B.D. Acharya endowment lecture. I met Dr. Acharya first time at one group discussion on sine graphs organized by Professor G. Ravindra at Mysore during 2005. Since then, in the conference international conference organized at Dharwad, we were in close touch, even by mail and by phones. And many times, even by mail, he was communicating several open problems to me. So it is the honor, and I dedicate the talk in the memory of late Dr. B.D. Acharya. Thank you. Algebraic properties. I will like to give a short introduction of Professor R. Balkrishnan. Professor R. Balkrishnan is an adjunct professor of mathematics at Bharatidasan University, Tiruchinapalli. He retired as professor and head of the department from Annamalai University, Tamil Nadu. There he worked for 13 years. He was also the Dean of the Faculty of Science at Annamalai University. He is the author of a very popular book, a textbook of graph theory, which has been published by Springer and has seen the second edition.
He is also a co-author of 2 forthcoming books on foundations of discrete mathematics with algorithms to be published by CRC Press during the course of the year. His interest in graph theory includes graph coloring, cycles, labelings, spectral graphs theory, etc. I will like to request him to deliver his talk on some algebraic properties of nodal graph. Professor R. Balakrishnan.